Davey Kirkpatrick is going to talk to us about SphereX. And I will stand up when you're out of time.
Okay, thank you, David. So over the past 5 days, in your talks in slides for your talks, in your posters, we've seen a lot of very tortured acronyms. I would like to posit, this is the one that has the most pain. Okay, so SphereX is actually launching in 20 days, so later this month. And what I thought I would do for this talk is not tell you about all the great science that we built the survey on itself, but actually tell you about the data products, how we're going to process those so you can start thinking about the actual science you would like to do on them. Okay, so what is SphereX going to do? First of all, it's an all-sky, yay, spectroscopic, yay survey. A dream of mine since I was in grad school. And it's not just a narrow band of wavelength that we're covering. We're actually covering everything from 0.75 to 5 microns. And we're not doing this in the traditional fashion of dispersing the light with a grism or a prism, anything like that. We're using something called linear variable filters. So each one of our detectors has a linear variable filter in front of it. And depending upon where your object falls vertically on the array, you're sampling a different wavelength. So we will very slowly drift things across the array, actually in steps, and get different wavelengths actually observed in that fashion, and you build up the spectrum with time. The spectra themselves have resolving power of around 100, and I'll get to more detail on that in just a second. There are 3 adjacent fields of view on the sky. Each one of those fields of view has a dichroic that actually splits the light into 2 pieces, so we need actually 6 detectors to catch all that. And let me show here. The first field is split up into band 1 and band 4, and if you look at the table here on the right, you will see how those are divided up into wavelength coverages and also resolving powers. The second field of view is covered by bands 2 and band 5. The third field of view is covered by band 3 and band 6. And notice that the 4 short wavelength channels have the lowest resolving powers that go around from 35 to 41, and the 2 long wavelength bands have a resolving power of about 120. Okay, so here's a schematic, and this is not accurate, but I'll get to why it's not accurate in a minute. You'll see a star first appear, let's see here, in band 1, and then band 4. There we go. You see it's going to be sampled 17 times. And then at a different date, it comes into band 2 and band 5. And at a different date, it comes into band 3 and band 6. And down here at the bottom is just shown a model spectrum in black, along with the SphereX data points as they're slowly built up over time. So we get 17 exposures per array. Each one of those exposures is 112 seconds each. So the total number is going to be 120 exposures for the entire spectrum. And we are in an ecliptic orbit and low Earth orbit, so we get 1 full spectrum every 6 months, and we have a 2-year mission, so that's going to be 4 full spectra of every spot on the sky. Our pixel size is quite coarse at 6.2 arc seconds, but the best way to think about this is shown down here in the bottom right, and that is that SphereX is going to provide complete near-infrared spectra for every 6 arc second pixel on the sky. Okay, so here's an artist's rendition of SphereX in orbit. And we are orbiting the Earth, again in an ecliptic orbit, along the terminator of the Earth. So the sun is always going to be 90 degrees away from the field of regard. And now we're going to look out to see what SphereX is actually looking at. There's the sort of semi-conical field of regard, and you see it's taking 112-second image and then stepping, taking another 112-second image, stepping, taking another, and so forth. And if you've been careful in counting here, you notice it doesn't come up to 17. It only comes up to 5, 6, or 7. So the field of regard is moving fast enough that we don't get all 17 exposures at once. So we have very careful scheduling software that knows when to hit a field again and when to hit it on the subsequent orbits, things like that, so we get the full sampling of the spectra. Okay, so here's a simulation of what the entire survey pattern would look like after 2 years of surveying. And this is in one of the 102 spectral channels. And we have really 2 surveys going on here. The first is because we see the ecliptic poles every single orbit, and each orbit is about 90 minutes apiece, we get lots of coverages there. And this is a little bit like WISE, if you're familiar with the WISE orbit, except that what Spherix has done is it's concentrated most of its, what should I say, the abundance of its repeated observations at the poles themselves, because it can do a little shifting and pointing to do higher depth there. So what they've done this is for the extragalactic background light part of the survey, they have decided to hit the north ecliptic pole really, really hard here and concentrate all those repeat coverages right at the pole. And they've done something similar at the south ecliptic pole, except of course, if you're familiar with the south ecliptic pole, the Large Magellanic Cloud gets in the way, so they've kind of offset that because they don't want the Large Magellanic Clouds too close. Okay, so that's what this looks like. Here's the expected sensitivity in each Spherix band. And this is just magnitude on the left. In AB magnitudes, this is the 5 sigma limit. Notice that faint is up versus wavelength. And just showing at the top here where all 6 of our bands are for Spherix. At the short wavelength bands, we are comparable, or at least in the ballpark, with Pan-STARRS IZ and Y. I should mention also that the band here at the top in brown is the one for the deep survey, which is the ones at the poles. And the band here, shown in red, is our expected sensitivity for the all-sky survey, which is everything else, basically. Okay, so we are, for the deep survey, we're very similar, we're very comparable to Pan-STARRS. If you look down here for the all-sky survey, we're comparable to the capabilities for Euclid spectroscopic, and we're much, much fainter, we go much, much fainter than 2MASS. We are also comparable over here to what we get at WISE W1, but we're not quite as sensitive by magnitude or magnitude and a half at W2. The reason for that is that we're passively cooled for one, and the second is these are the 2 bands where we have the highest resolving powers. Okay, so here are 2 objects to show you what the sampling looks like over time. This is a year's worth of data. So the orange object is something that's close to the north ecliptic pole, which has lots of coverages. You see there's a lot of data there. For anything else in the all-sky survey, it'll look something like these blue dots here. So for the blue dots, you see this particular source was observed over the course of 16 days, and we got all of the 102 channels over that course of 16 days. When we saw it again, that piece of sky, 6 months later in this simulation, it took us more like 3 weeks to get everything. We got the same sampling of data once again. It's a different actual sampling, but we got the same set of 102 data points. Okay, let me talk a minute about the data processing and the data products. So the algorithms have been developed in collaboration with the Spherix science team. Level 1 processing is basically just taking the science and the telemetry data, stitching those together into FITS files, doing coarse astrometry corrections and reference pixel corrections. Level 2 processing is where we actually create calibrated linear variable filter images, and those are sent to the URSA archive. And this is where everyone should pay a lot of attention here, because these are going into the archive within 60 days of them having been taken and processed. So these are going to be the first data products you will see from Spherix. Okay, we go on and process other levels too. There's a level 3 processing, which actually takes the spectral measurements, and those will create the 102 all-sky data cubes, and those will be part of the year 1 and year 2 data releases. In addition, there will also be these high reliability source catalogs, and the sources will be selected from the Spherix input catalogs, which have hundreds of millions of sources in them, and those where we go into the data cubes and actually determine the spectra of all of those, or determine the individual photometry for all of those. And that photometry is going to be tabulated in both the native wavelengths where they were taken and binned over the 102 spectral channels that we've set up as sort of the standard 102 spectral channel grid. And this high reliability source catalog is going to be created after the third sky survey and again after the 4th sky survey. There's also a series of legacy data products here that will also be produced, and those have to do largely with the 3 main science focuses of the program. But I want to talk about one that's not one of the main 3 science focuses of the program, but is something that Rachel Akeson, myself, Mike Werner, and a postdoc to be named very soon are working on, and that's something called the Precision Stellar Properties Legacy Catalog. And the science goal here is to actually enable a critical increase in the precision of stellar parameters for low-mass stars and brown dwarfs. And for this team, this group of people here in attendance at this conference, it's really to increase the precision of parameters for your exoplanets. And I'll talk about a little bit more about that here. This is a very wordy slide, which I think I'm going to skip in the interest of time, and I'll go directly to the next one to talk about what we're actually doing, how we're building these catalogs for this particular legacy product. So the target catalogs for the first part is an potential exoplanet host star catalog. And what we've done here is we've taken the 200,000 stars from Kepler DR25, we've taken another 200,000 stars from K2, and we've taken the list from Plato, which is more complete than the test sample. We have about 2.4 million FGK dwarfs and subgiants in that list, and about 300,000 M dwarfs, which gives a total unique count of just under 3 million sources. So that is all for potential exoplanet host characterizations. We're also supplementing that with the 20 parsec sample that I published last year, which is all the stars and all the brown dwarfs within 20 parsecs. And this is sort of a fiducial sample where we know the parallax is very, very well. We've characterized the objects very, very well. In many cases, we know exactly what the stellar multiplicity is, or the multiplicity with brown dwarfs and that sort of thing. So there are, in that sample, 3,000 stars, if you cut it spectral type M9.5, and brown dwarfs is about 600 of those. Okay, so legacy products, what are we going to produce from this? So the SphereX data are coming into play because we're taking the SphereX data and we've got, at least for the 20 parsec sample in particular, we have bolometric luminosities there. And we can also have distance estimates for everything in these other lists as well. So with the bolometric luminosities for the exoplanet host stars, what we're doing is we're taking the SphereX data and also fitting it to model grids to try to get effective temperatures out that are very precise. And then using the Stefan-Boltzmann relation, we're actually getting radii for those stars. Those radii are going to be about a factor of 10 better than we currently have. This is going to be over a very large, very homogeneous data set. And that will apply directly to improving the radii on your exoplanets. Okay, for the brown dwarfs, we're doing something slightly different, which is we're also computing the bolometric luminosities, but in the case of old brown dwarfs, we know already what the radii are. There should be, because of degeneracy pressure, approximately 1 Jupiter radius. So from there, you can get effective temperatures because our model grids for brown dwarfs are not so good at the moment. So here we're getting effective temperatures that are going to be accurate for probably one of the first times. Okay, and I'm a little bit out of time, so there is a number of things that I should point out here, probably in the question and answer session as far as tools you can use on the data once they're available. But I would like to point out the link at the bottom here. If you go to the URSA website, /data/spherex/WASJAN 2025. There are some sample data sets there that you can already start to play with. So you have a leg up when these things start coming out in about 100 days from now, or 120 days from now when they start appearing in the URSA archive. Okay, here's our timeline, and I'll leave it there. I'll take questions. Thank you.
All right, there's a question right up front. Sean?
Great talk. I was curious, is there any potential for an extended mission? And if so, do you have a certain pointing idea in mind?
I didn't hear the very last part of that, sorry.
So yeah, is there an extended mission possible? And do you have any preference for how to point it?
Preference for the pointing?
Yeah, like
Okay.
Would you do an all sky?
Okay, so as far as the extended mission goes, we have no expendables on board. So it is possible to have an extended mission here, and people have already started thinking about that. As long as we meet our expectations, I think there's a good chance we will at least have a shot at an extended mission. As far as the surveying the sky, as far as I know, we're kind of kept to that same Terminator type orbit, and you saw what the field of regard was. I forget exactly how wide that is, but you can kind of tell from the size of the detector it's not very broad. So we can deviate within there a little bit, but not by very much. So I wouldn't expect great changes to how the survey data taking would undergo in an extended mission versus what we have in the prime mission.
Ward?
Ward Howard, CU Boulder. Given the survey strategy that you were laying out, you're likely to get around order of 10 to the 4 or more stellar flare spectra just by serendipity. Do you have any plans for how you're going to be producing your fiducial spectra given the activity from some of your stars? And then also, do you have plans to do astrophysics with some of these chance events?
Okay, so I missed a couple of words there. Were you talking about variability in general, or?
You should pick up somewhere around 10 to the 4 to 10 to the 5 large stellar flare spectra.
Oh, flare spectra. Okay, that's the part I missed. We don't have any plans specifically for that, but they will jump out of the data as changing from sky pass to sky pass. Mm-hmm. And as far as I know, that will be flagged within the data stream itself as being discrepant. So there will be plans there. There are tools available for you to actually identify those objects.
Thank you.
Okay, I'm sorry, we're going to have to leave it there, and let's thank Davey.